Lesson 6 is a continuation of Lesson 5. In Lesson 5 we worked with z-scores and the bell-shaped curve, and we're going to continue that in Lesson 6. Now Lesson 6 is a little bit more real life, where we're actually going to be taking samples. And the things we need for Lesson 6 are your TI-83 calculator, and again the same normal distribution chart or bell-shaped curve that we did in Lesson number 5. So sample size. When you take a sample, now remember, a sample is a subset of a population. And again, it says here in Lesson 5 we learned how to use a normal distribution when given a mean and standard deviation. The examples used in the last lesson were for all people or things, which are populations. We had examples of all people have an IQ, all hotel rooms, the response time for all police, etc. Now we'll be taking a sample from a population, but there are certain restrictions when picking a sample. So we're going to be doing samples this lesson. First restriction, number 1, the sample size must be selected randomly. We talked about that earlier. Randomly means each item in the population had an equal chance of being picked. Typically this is done by the use of a computer generating random phone numbers within each area code. These are again called random number generators or random digit dialers. Another way of saying that is random digit dialer, or RDD, as they say in real life, RDD. Very important now, the minimum sample size is 30. You can have more, but the minimum is 30. So if another teacher in another class is asking you to do a research project and they say, we'd like you to go out and sample some people and get what their feelings are about something, the minimum you're going to sample is 30. Of course, more is better because you get more information, but the minimum should be 30. The maximum sample size is 5% of the population size. So staying within these minimum and maximum sample size keeps the sample being normally distributed. Straying outside of these minimum and maximum values leads to bias in the sample. So right now we have a minimum of 30 and we have a maximum of 5% of the population. So that's anything within the minimum and maximum would be considered statistically proper. So, the results of a sample are just as accurate as that of a population. We're going to learn that a little bit later. Selecting a sample instead of a population saves time and money by asking fewer people or things questions than that of a population. Just makes sense. So you'd rather sample 30 people than 3 million people when the results are pretty much the same, because it's going to save you time. You don't have to spend as much time asking 30 people a question. So, what are the minimum and maximum statistically allowable sample sizes taken from the following population sizes? A company has 1,200 workers. Well, again, the minimum is going to be 30 no matter what. It's always 30. The maximum is going to be 5% of the total population size. So there's 1,200 workers at this company, and 5% will be written as a decimal, 0.05. And when we multiply 0.05 by 1,200 in your calculators, we're going to get back 60. So any sample between 30 and 60 workers will be statistically correct. Again, the more, 30 is okay, but 35 is better. 40 is better than 35, 50 is better than that. All the way up to 60 would be the best sample size. Now you have a choice. Either conduct a sample within this range, so sample anything 30 to 60, or ask all 1,200. Those are your choices. There is no other choice. So number 2, how about we want public opinion from within a metropolitan area comprising 850,000 people. Again, if we want to conduct a sample within this population, the minimum is 30, and then the maximum will be 5% of 850,000. That's going to give you back 42,500. So again, the minimum is going to be 30. The maximum is going to be 42,500. So anything within that range is okay. The more people, the better for more information. Or ask all 850,000 people. Those are your choices. This would be better simply because it's going to take you less time and effort to ask within this range, so long as the people are asked randomly. than to ask all 850,000 people, especially when the results from whatever sample size you pick here are going to be almost as accurate as everybody. And realizing that the more people asked within this sample size, the more accurate you're going to be towards everybody. So if you sample 30, 40 people are going to be more accurate than 30 because you have more information. And 100 will be better because more information, all the way up to 42,500. Anything within there. Typically in real life, usually that samples conducted by Roper and Gallup and Marist and all those organizations usually sample anything from 800 to 1,200 people. Some usually within that range. You can always do less, you can always do more, but that's usually the standard that we have. All right, so if we ask a third question, again, we want to know what the sample size is. Finding defective parts from an assembly line that makes 10,000 parts a day. So, you know, as they're making the parts, they randomly select parts off the assembly line when they're complete, and they take a look and see if there's anything wrong with it, any defects. And it could be in the way it looks, it could be in the way it operates. And again, the minimum that you would sample in that day would be 30. The maximum that you would sample would be 5% of the 10,000 total, which would be 500. So anything within 30 to 500 would be statistically correct. You would never sample 10,000. That would just slow down the process. You wouldn't sample every single part. That's just crazy. So now here's the way sampling actually works. So that gives you the sample size. So you get an idea of what large sample you can actually collect as far as information. The next one is sampling from a population. Here's how it works. Let's say we ask a random sample, keyword there is sample, of New Hampshire police departments, and they claim that they had the following cases of larceny in the past few years. In 2011, we got back a mean of 1383 with a standard deviation of 1671. And then in 2012, they got back 142. And then in 2013, they got back 131 with that sample size. So the way this works is, in order to sample everybody, you're going to assume, because it's a sample, now you're going to assume all New Hampshire police departments, and you're going to say the average is going to be 1383.5. Here you're going to say the average is 142.7, and here you're going to say the average is 131.67. Whatever the sample mean is, that's going to be assumed to be the mean of all, in this case, New Hampshire police departments. You have no other thing to go by. So that's just the way it works. If the sample size, let's say, was 35 police departments, then what you have to do is you have to change the standard deviation from the sample to get the standard deviation of all. So the only thing that's going to be changed in these cases is the standard deviation. So the standard deviation is going to be the standard deviation of your sample, but then you divide by the square root of the sample size. And I'll show you how this works. So in our calculator, the standard deviation is going to be 16.71, and we're going to divide that by the square root of the sample size, which is radical 35, and we're going to get back 2.82. So this is our new standard deviation. Again, we can never use the standard deviation of a sample when we're trying to make predictions as to the outcomes of the population, so we have to change the standard deviation. So in the case number 2, where the mean is 142.7, we're going to keep that as the mean. But the standard deviation of 23.56, we're going to change to 23.56 divided by radical sample size. And if the sample size is 35, so then we would say, here's my calculator, 23.56 divided by radical sample size. And we're going to say 3.98. We're going to go 2 decimal places. And so this would be our new mean, and this would be our new standard deviation. Mean, standard deviation. For the third example, the mean stays the same, but the standard deviation we're going to take of the sample and divide by radical sample size. So we're going to take 26.59 and we're going to divide by radical sample size. And we're going to get back 4.49. So in general, whatever the sample is, okay, you have a sample mean here and a sample standard deviation. When you're trying to guess as to the population, the mean stays the same, but we now label it mu sub x bar. Okay, that means that means the mean of all items in a population. And now here's the difference. The standard deviation of the population, you take the standard deviation of your sample and you divide by radical n, which is square root of sample size. Now I know this looks a little confusing right now. This happens all the time in my regular stats class. What'll happen is we're going to do a bunch of examples, and after about the second or third example, you realize, oh, I get it. It's just a quick little formula that we're going to use for every question. So here's a question. A sample of 85 people's blood glucose level after a 12-hour fast has a mean of 85 milligrams per deciliter with a standard deviation of 25. Okay. What percentage of the time will another sample of 85 or all people have a blood glucose level of? Well, there's a couple questions in here. Number one, the key word in here is sample. If it says a sample, that means we must change the standard deviation. That's the first thing. Have to change the standard deviation, number one. Okay. So, number two is the fact that the sample size is 85, which is 30 or more, means that this is going to create a bell-shaped curve. And that'll allow me to use my z-score chart that I used in the last lesson that we also covered in lesson number 5. So here we go. Step 1. We want to know what percentage of the time will another sample. So step number 1 for all of these is find the mean and standard deviation and use formula for standard deviation. So the mean is mu sub x bar. This is the mean that they told you in the problem, because it can't be different. If they sampled 85 people and they got back a mean right here of 85 for their glucose level, then that has to be the mean of everybody, because if you change that number, then you have nothing to go by. I mean, if that's what the sample mean was, then you just assume that that's the mean of everybody. Okay. But the standard deviation, however, because it's a sample, I'm going to take the standard deviation of my sample right here. Standard deviation is 25, and I'm going to divide that by the square root of the sample size. And it said there was a sample of 85 people, so that's my sample size. And I'm going to put that in my calculator. So 25 divided by square root of 85. Okay, there we go. 2.71. So that's my mean, and that's my standard deviation. This standard deviation in the problem is now dead. In terms of we don't use it anymore. That's it, it's out. So step number 2, using the z-score formula that we did in the last lesson, data minus mean over standard deviation, we're going to find the z-score for the question, and the question asks for more than 90. So the z-score is going to be data, which is 90, subtract the mean, which is 85 from the question, and we're going to divide by the standard deviation that we just found a second ago, 2.71. Okay, so here we go. Clear the screen. 90 minus 85, okay, divided by 2.71. And we get back 1.845. Let's round that to 1.85. Now this is my z-score. So now the question says more than, and so we're going to draw ourselves a bell-shaped curve. We always label z to be 0 in the middle. Here we go. We're going to positive 1.85 is my z-score from the question. We want more than that, so we're going to go more than that. And remember, the shaded region does not cross over 0, so we're going to subtract, and the tail, so 0.5 is going to be included in the question. And I'm going to grab my bell-shaped curve chart. Hold on one second. Okay, we're looking up 1.85. So here we go. We go down 1.8. We work our way over to 5. Okay, and you see 0.4678. That's 4678. Whoop, nope, I'm looking at the wrong one, sorry. 1.85 is 46. Oh, that's right, 4678. That goes between 0 and 1.85. Okay, so we're going to subtract 0.4678. 0322. That's the probability. And we're going to say 3.22% is the chance that the average of another 85 people will have a glucose level greater than 90. Okay. Let's take the same question. Same mean, same standard deviation. And what if we ask, what's the chance that the average will be less than 92? All right, again, same 3 steps. Find the mean. Well, the mean we already know. U sub x bar is 85. The standard deviation, sigma sub x bar, we found from the last question was 2.71. So we're going to find the z-score for the data. So 92. So data, 92, minus the mean, 85, divided by the standard deviation of 2.71. So here we go. 92 minus 85 divided by 2.71. We're getting back 2.58. That's the z-score. We would like less than that because that's what the question is asking for. So if we draw ourselves a bell-shaped curve, positive 2.58 is our z-score. We want everything less than that, which is all the way left. Okay. We look up 2.58 in our bell-shaped curve chart. So there's our bell-shaped curve chart. We go down to 2.58, 2.5, work our way over to 8. There you go. We're looking at 0.4951. That goes between 0 and the number we just looked up. The left half is 0.5, and if we add the 0.5 to the 4951, we're getting 9951 is the probability. So 99.51% is the chance that the average glucose level will be less than 92. All right, let's look at the next one. How about between 75 and 80? Well, this is like the last section that we did. We have to find 2 separate z-scores. So we have to find the z-score for 75, so data 75, minus the mean, which we found to be 85, divided by the standard deviation. And then we have to separately find the z-score for 80. So 80 minus mean, 85, divided by standard deviation, 2.71. Okay, so we're going to go 75 minus 85 divided by 2.71. We're getting back negative 3.69 here. And then we're going to say 80 minus 85 divided by 2.71. Negative 1.845. So we're going to call it negative 1.85. We want between these two values. Okay, so negative 1.85 and negative 3.69. We want between those two. The area I'm looking for does not cross over 0, so I know I'm going to have to subtract. And the tail is not part of it, so 0.5 is not involved. So we're going to look up separately now in our bell-shaped curve chart. I'm going to negative 1.85. So we go down 1.8, we work our way over to 5, and we're getting back 0.4678. That's between 0 and that number. And then when we look up 3.69, we're getting back 0.4999. So we know that this area here plus the shaded region is 49.99. So if we take the 49.99 and subtract the 46.78, we're getting back a 1 and a 2 and a 3 and a 0. So 3.21% chance the average glucose level, I can't say that, glucose level, is between 75 and 80. So that's the average. Okay. We have to always take guesses on what the sample is because earlier the question said a sample of 85 people got back a glucose level of 85. Well, we assume that that's what the population average is, but we're not 100% certain since we didn't ask everybody. So there's chances that the glucose level could be different. There's chances it could be less than 92. There's chances it could be between 75 and 80, and that's what we're trying to figure out right here. All right, here's another one. Let's read this one here. A sample of 47 days shows a police response time average of 8.4 with a standard deviation of 1.7. All right, what is the percentage chance that another sample of 47 days shows a police response time of more than 8 minutes? All right, so first thing you got to realize is the question says sample. Sample means we have to change the standard deviation. It also says that a sample of 47, since 47 is 30 or more, this whole thing creates a bell-shaped curve. So we can use our bell-shaped curve chart. All right, step one. Find the mean and standard deviation. It's probably a good idea right now to pause the video, come up with those answers on your own, and then start the video back up and see if you're right. Okay, hopefully you found those. And the mean, mu sub x bar, is the same mean that they said in the question, which is 8.4 minutes is the response time. So that's our mean. Our standard deviation, sigma sub x bar, is the standard deviation in the question, which is 1.7. But because it's a sample, we have to divide that by the square root of the sample size. The sample size was 47 because it said a sample of 47 days. So in our calculator, we're going to put in, okay, here we go, 1.7 divided by the square root of 47. And we're getting back 0.247. Let's call that 0.25. So that's our mean, and this is our standard deviation. Now we can answer the question. So step number 2, using the z-score formula, data minus mean over standard deviation, find the z-score for the question. So we're asking more than 8 minutes. So let's find that z-score. Data, 8 minutes from the question, minus the mean, 8.4, divided by the standard deviation of 0.25. All right, let's figure that out. 8 minus 8.4 divided by 0.25. Okay, so we're getting a z-score of negative 1.6. And they're asking for more than in the question, so we're going to say what's more than negative 1.6. Here we go, bell-shaped curve. Z-score is negative 1.6. We want more than that. Okay, we know that the right hand to the right of 0 is all the way over, so that's going to be 0.5 or half the bell-shaped curve. When we look up 1.6, bring the chart in again. When we look up 1.6, we get back 0.4452. That goes between 0 and the number. And that plus that is going to give us back 0.9452, or there's a 94.52% chance the average response time is more than 8 minutes. So there's a good chance that the average response time is going to be more than 8 minutes in this particular police department. Okay. So now, same question. Part B, we're just going to ask for different results here. What's the chance that the response time was less than 7 minutes? I'm just going to copy over now. We already found the mean, and that turned out to be 8.4 minutes. And previously we found the standard deviation to be 0.25. Okay, so we got to find the z-score. So we just copied down the mean and standard deviation from all the work we did with Part A. All right, we want to know the question less than 7 minutes. So we're going to find the z-score, 7 minus mean of 8.4 divided by standard deviation of 0.25. 7 minus 8.4 divided by 0.25. Negative 5.6. We want less than that. Negative 5.6 is a negative, so we put it on the left. Less than is always left of that. So we're looking at a tail, left tail. The shaded region we're looking for does not cross over 0, so we're going to subtract. The tail is involved, so 0.5 is going to be included in part of our answer. We're basically just going to subtract now, looking up the z-score. And remember, our chart doesn't go all the way to negative 5, so we just use the bottom. It says for anything greater than 3.70, we use 0.4999. And so here we go. 0.4999. So 0.0001 when we subtract, we move it over 2 decimal places. And there's a 0.01% chance, so it's very unlikely the average response time is less than 7 minutes. How about if we ask for a new question, within 1 minute of the mean? Well, we found earlier that the mean right here, the mean is 8.4. We want to be within 1, that's left and right of that. So within 1 to the left, so 8.4 minus 1 is 7.4, and then 8.4 plus 1 is 9.4. So they're basically, same question would ask, what's the chance that the average is within these numbers? So we're just going to find 2 z-scores. We got to find the z-score for 7.4. So data 7.4 minus the mean 8.4 divided by standard deviation of 0.25. And then we find the z-score of 9.4 divided by the standard deviation. So let's get those numbers. 7.4 minus 8.4 divided by 0.25. We're getting back negative 4. And we should get positive 4 on the other end because it's the same difference, but let's do it anyways. 9.4 minus 8.4, new data 9.4, divided by 0.25, we're getting back positive 4. These are our z-scores. Okay, so we have to look up those z-scores, and again, both of those, z-score of negative 4, z-score of positive 4, are off the chart. There is no z-score of 4 and negative 4, so we're going to use 0.4999. 4999 over here, and 4999 over here. Here he goes between 0 and the number we looked up. So if we take 4999 and add the other 4999, we're looking at 0.9998, or 99.98% chance that the average response time in this particular police department will be within 1 of the mean, which was 8.4. All right, let's do another one. Okay, so let's read. And it says, the average life before replacement of a refrigerator is 14 years, and the standard deviation is 3.6 years. Based on an N, well now N you know means sample size, of 72 refrigerators. What is the percentage chance that another sample of 72 will have a life before replacement of between 15 and 16 years? Okay, so how about you pause the video, see if you can answer this question, and then come back. Okay, so it's 3 steps. Step 1, find the mean and standard deviation. The fact that it says sample right here, that little n means sample. Sometimes they put the word sample in the question, sometimes they use n. We need a mean of mu sub x bar, and the mean is 14. Okay, and then we need a standard deviation, which is the standard deviation 3.6 divided by the square root of the sample size. And they said the sample was 72 refrigerators. 3.6 divided by radical 72.42. Okay, step 1 is find the mean and standard deviation. Step 2, find the z-score. We have to do it separately because they want between 15 and 16. So the data is 15, and we subtract the mean, which is 14, and we're dividing by the standard deviation of 0.42. And then the data is 16 minus the mean 14 divided by 0.42. So let's find those. 15 minus 14. 2.38 for this one. And then 16 minus 14 divided by 0.42, 4.76. So we want between those two z-scores. Zero always goes in the middle. 2.38 for a z-score, 4.76 for a z-score, and we want in between those two. The shaded region that we want between the z-scores does not cross over 0, so we're going to subtract. And the tail's not involved, so 0.5 is not part of the final conclusion. And we look up 2.38. So I'm looking on my bell-shaped curve right now, 2.38. We're getting back 0.4913. And then when we look up 4.76, that's actually off the chart. So that's 4999. So we take the 4999 and we subtract the 4913. We're getting back 6800. So 0.86% chance that the average life before replacement of a fridge will be between 15 and 16 years. So it's not likely that the average. That doesn't mean that there's a 0.86% chance that your fridge is going to live between 15 and 16. Your personal fridge. That means the average of 72 fridges. You take all 72, see how long they live, and the average of those 72, there's a 0.86% chance that the average of those will be between 15 and 16. Okay. How about we word the question like this? What's the chance that the refrigerator's average life before replacement is greater than the mean by 1.5 or more? Well, that's a fancy way of basically saying 1.5 years more than the mean or more than that. So we got back the mean from the last question to be, let's see, take a look, it was 14. So we want 1.5 or more than that. So if we add 1.5 to 14, we get 15.5 or more. That's really what we're asking for here. Greater than the mean by 1.5, so that would be 15.5 or more. Okay, so let's find the z-score for 15.5. Data minus the mean divided by the standard deviation, which we know is 0.42 from the last question. All right, so let's find this. 15.5 minus 14 divided by 0.42. We're getting back 3.57. So we want 3.57 or more. Okay, 3.57 or more. We look up 3.57 in our bell-shaped curve. We're getting back 0.4998. And we know that from the mean all the way over to the right is half. And this plus the shaded region is half. So if we take half, we take away the 4998. 0.0002 or 0.02% chance that the average life before replacement of a fridge will be 15.5 or more. Okay, so that's basically how everything is done in terms of sampling. Okay, from the sample you get an average, and you assume that that's the average of the population, and it's also giving you a standard deviation. You have to use a formula to change that standard deviation. And then from there you just do what we did in chapter 5, or lesson number 5, excuse me, where we find the z-score and then we use the bell-shaped curve chart. Now, there's 2 ways to do samples. That was the first way, where we're dealing with something that I like to call values. Anytime you have a value, the mean is mu sub x bar, and the standard deviation is the formula we just did a second ago. Values would be anything that comes out to be a number. So like if we talked about waist size of females or males, the waist size is going to be a number. You know, the waist size is, for a woman, it could be an 8 or a 9 or a 10. You never put a percentage on that. You don't say my waist size is 8% or 9% or 10%. Or we could say how long it takes to get to work. So time to work. That's a value. The outcome would be a value because it's going to be minutes or hours or something like that. You wouldn't say how long does it take you to get to work? You wouldn't say it takes me 12%. That just doesn't make sense. You would say 12 minutes or 12 hours or 12 seconds or something along that line. The next then talks about what if the outcome is a percentage. So that's the second. There's only 2 types. There's value and then there's percentage. So here we talk about statistical outcomes can be either a value or a percentage. Like I said a second ago, typical questions that have a value outcome are: what is the average waist size? What is the average shoe size? What is the average number of cases adjudicated by a DA's office? Typical questions with percentages are usually opinion, but not always, such as what is your favorite color? What is your favorite alcoholic beverage of people 35 and over? What is the recapture rate for escaped convicts? Recapture rate would be a convict that gets out and then does something bad and has to be arrested again. So you would say that would be 12% of convicts or 15% of convicts. So what we have here for percentages is from the sample, they use the letter P, which means percentage. So they pick a nice letter for us to make sure that we understand it's a percentage. Okay, so all of these should have a hat on them. I couldn't put a hat in the Word document, so I figured I'd write it in here for you. The way it works with percentages is there's just a different formula for standard deviation. For example, if we ask somebody what their favorite color is, this is based on a sample, so they're saying there's 1,062 people, and we got back the answer of 32% of people said their favorite color is blue. So what we would then say is, if this is our sample, we're going to use that to guess what our population is. Oops, let me scroll up a little bit. So this is our population. So we're going to say the percentage is the same percentage as we just found. If 32% of people say their favorite color is blue, then we're going to say 32% of the entire population says that the percentage of their favorite color is blue. But now this is my standard, so this is the mean. And then sigma sub p hat is our standard deviation. So the mean is called mu sub p hat. Let me write it a little bigger for you. Mu sub p hat. And then the standard deviation is called sigma sub p hat. Now this is a different formula. This is the square root of p times q over n. Now what do those letters mean? The p is the percentage that we got back in the question 32. Q would be if 32% of people say blue, then the opposite of that would be everybody else. So if 32% say blue, then 68% of people are going to say not blue. We multiply those two numbers together, and then we divide by the sample size, which, if you notice up here, 1,062. Now this is a little different. We're taking the square root of the entire thing, where earlier we're just taking the square root of the denominator when we're dealing with a value question. All right, so here we're taking the square root of the whole thing. So let's take a look and see what that is. So we're going to hit the square root first, and we're going to have 32 times 68 divided by 1,062. So there we go. Okay? And we get back 1.43. So if we're dealing with a question about favorite color, we would have a mean of 32, and we would have a standard deviation of 1.43 for that question. If we ask a sample of people what is their favorite alcoholic beverage, and we get back an average of 45% say wine, okay, this would be our mean of the sample, and it's based on a sample size of 864, then we're going to say the mean of everybody, which is mu sub p hat, this is the mean of the population, is still 45%. And then we're going to say the standard deviation, which is sigma sub p hat. Because it's a percentage, we use the formula square root of p, which is 45%, times q, which is 55%. And we divide that by the sample size, which is 864, because that's what we set up here. Okay, so in our calculators, we put in the square root of 45 times 55, divide by 864. 1.69 is our standard deviation. So let's do another one, recapture rate. Let's say the recapture rate is 76% with a sample size of 6,150 convicts. Okay, so this is our sample. Now we're going to make the assumption that that is now true not just for these convicts, but this is true for all convicts. Then we're going to say the mean of all convicts is mu sub p hat, p for percentage, and that's going to be 76%, because that's what we got back for our sample. We're then going to say the standard deviation is sigma sub p hat, and that's going to be the square root of p, which is 76, times q. Now if 76% are recapture, then everybody else would come up to be 24%, and you divide that by 6,150. Okay, so square root 76 times 24 divided by 6150, 0.54. Now this is just step one in the process, which is find the mean and standard deviation. So the first thing I'm trying to introduce to you is the different formula for percentage for standard deviation. There's a different formula. Now we can actually do some questions now that we have the formula down. So let's flip over here. Let me show you a few questions. Okay. So here we go. A sample. Now we circle the word sample, and that means we have to change the standard deviation. Okay. For 1,012 people found, 66% of U.S. adults use alcoholic beverages. All right, so what's the percentage that it could be different than 66%? What's the chance it could be more than 70%? Well, we're going to use the same steps that we did just a second ago. So step one, find the mean and standard deviation. Now this is percentage question because you see a percentage in the actual question itself, in the statement. So the mean, because it's a percentage, we're going to say is mu sub p hat, and we're going to say that that is 66. So that's our mean for the question. Our standard deviation, sigma sub p hat, is going to be square root of p, which is 66, times, if 66% use, then 34, because it has to total 100, do not, and we divide that by a sample size right here of 1,012. All right, in our calculators, we put in the square root of 66 times 34 divided by 1,012. Okay, and we get back 1.489. Let's call that 1.49. And that's our standard deviation of this question. So step one is the same step one that we did previously. The only difference is now there's a different formula because it's a percentage question. Step two is the same thing. Find the z-score. So z-score is still data minus mean divided by standard deviation. The data is the question, 70, right here. We're subtracting the mean, which is 66, and we're dividing by the standard deviation of 1.49. 70 minus 66 divided by 1.49. 2.68 is our z-score. We want more than that because that's what the question asks for. Draw ourselves a bell-shaped curve. We want more than that to the right. Okay, we look up 2.68. Okay, 2.6, we go to 8. We're getting back 0.4963. That goes between 0 and the number we just looked up. Again, this plus the shaded region is the right-hand half, so we take half, take away the 49.63, 0.0037. So there's a 0.37% chance that the percentage of adults that use alcoholic beverages is more than 70%. So greater than 70% use alcohol. Okay. What if we ask a different question? Now these questions all turn out to be the same. Every time you have a statement, these questions either ask for less than, more than, or between. Less than, more than, and between. That's the only three questions you can ask. So we just asked a more than question, so now we ask a less than question. What's the chance that it's less than 68? Step 1 is find the mean and standard deviation. We already have the mean and standard deviation because that's based on the question. 66% said they use alcoholic beverages. Got it. So what's the chance that it's less than 68? So we can go right now into data minus mean. So the data is 68. The mean is 66. The standard deviation is 1.49. All right, so 68 minus 66 divided by 1.49. 1.34. That's the z-score. We'd like less than 1.34. 1.34. We want everybody less than that. Okay. We know we have the left half here is 0.5. We look up 1.34 in our bell-shaped curve, and we're getting back 4099. And so the shaded region is going to be 0.5 plus 0.4099. That's going to be 0.9099. Or there's a 90.99% chance that less than 68% of people use alcohol. Cool. What's the chance that it's between 63 and 69%? All right, so we got to find two separate z-scores. We got to find the z-score for 63. We already know the mean. We already know the standard deviation because we already calculated that based on the question for number 1. So we're just going to repeat those. Data, 63, minus the mean, 66, and the standard deviation is 1.49. We do the same thing with 69. Okay, so 63 minus 66 divided by 1.49, negative 2.01. And then we find 69 minus 66 divided by 1.49, and we're getting back positive 2.01. Okay, so let's draw ourselves a bell-shaped curve. 0 always goes in the middle. In this case, I put in the z-score we found for 63. I put in the z-score we found for 69. We went between those. And when we break it up at 0, when we look up 2.01 in our bell-shaped curve chart, we're getting back 0.4778. And it just so happens that that's the same number on both sides because it's the same z-score. And so we're going to add 0.4778 with the other area, which is also 0.4778. And we're going to get 16 and 1 is 15 and 1 is 15 and 1 is 9. So 95.56% chance that between 63% and 69% of U.S. adults use alcoholic beverages. Okay. Let's take a look at another question. So number 2. The percentage of Americans in favor of making smoking totally illegal is 19%, and that's based on N equals 864. Of course, that N means sample. Okay. What is the percentage chance that the percentage of Americans who want smoking totally illegal is? Okay. And again, you can only ask 3 questions, less than, more than, in between. I'm going to ask the first question is going to be a less than, this one's going to be a between, and then this one's going to be a more than. So here we go. Step 1. We have to find a mean. And so mu sub p hat is our mean. And when we read the question, it says the percentage of Americans in favor is 19%. So there's our mean. And it has to be given in the question. The standard deviation, because it's a percentage, is the square root of p, which is 19. So if 19% are in favor, everybody else then would be not in favor, which would be 81. And that's divided by the sample size of 864. Okay. So we want the square root, 19 times 81 divided by 864. We're getting back 1.33. Now that's the standard deviation. That's not a z-score. So there's my mean. There's my standard deviation. We're going to use that mean and standard deviation for every question that follows. Okay. So step number 2, find the z-score. So the z-score is data, and that's the question, so 23, minus the mean, 19, divided by the z-score of 1.33. So 23 minus 19 divided by 1.33. 3.01 is my z-score. So 3.01, we want more than, nope, I'm sorry, we want less than that. Cross that, less than. So that's all of this over here. Okay. So that would include the left-hand half of the table, or the bell-shaped curve. We look up 3.01, we're getting